In this video I'll do another test of my mystery battery here. This time I'm going to do a capacity test. So I want to discharge it down to flat and then charge it all the way up, see how much capacity it actually has. I have some theories, we'll see if they hold true. The setup at the moment is that I have my BMS modules connected up to the individual cells. The battery here is supplying power through this lead, through a fuse underneath, and through this isolation switch. Then out through this wire. You can see this is a lot smaller than this. I'm not going to be doing as much current with this particular test. And this goes, so the other one, the positive terminal, goes through that red wire and through this relay that I have here. And then through the blue wire there. And so you can see here at the moment we've got 0 volts. If I enable it, we now have 20.9 volts there. So this is where I'm going to put my load for discharging. At the moment I've just got it set up so we can test out to make sure the setup works. I need to stop this when any one cell gets too low a voltage, and the way that I'll do that automatically with the battery management system. So if we go and have a look over here, the BMS master is set up here. I've got it connected, it runs off 12 volts. I've got a 12 volt battery there. Because this test's going to go for a while, I've got a power supply there set to 13 volts to keep that nice and healthy. And then on the computer, these cells I think are probably quite similar to the LG E63 cells that I've used in the electric Brumby. And this table is from the E63 cells. Assuming that they are very similar, then this table should be very similar. And what we have here is state of charge in this column and this column. It's sort of a two split table. And at 100%, a cell voltage is 4.166, and at 0%, cell voltage is 3.167. Now, my cell voltages at the moment are 3.50, which puts it around here just over 15%. What I want to do is to discharge it until we reach 0%. To stop it when we get to this voltage here, I've set up my battery management system to stop literally when we get to 3.167 volts. I'll also be using this computer to log the voltages as we go, because you can see as you discharge here, we've got 3.5, each of these steps is 5% state of charge. We've got 3.5, 3.5, 3.5, 3.4, 4, 4, and then suddenly we're off to 3.1. So the voltage does drop off sharply in this last 5% here. I'm going to be looking for that in the voltage that I'm logging on the computer. If I see that at that point, then I'll have an idea that this is using the same chemistry, and we can probably treat the cells similar to what is in the specs for this particular cell. Now I'd like to do a test to make sure that this system disconnects when we do get to the low cell voltage. So what I've done, I have this relay here, so the BMS is controlling this relay, and so we're discharging the battery through this relay to the load, which we'll get to in a second. But what I've done at the moment as a test is I've hooked up this last BMS, so all the other 5 are connected up to the cells here. The last one would normally be connected up to the cell, but I don't have it connected up at the moment. I have it connected up to this power supply here. And so at the moment I am supplying this particular module with 3.83 volts. Looking at the display on the master unit, you can see 3.50 is the lowest, 3.82 is the highest, which was what is shown on the display over there. I'll use this as a test. I'll take this one down to 3.1 and make sure that the relay opens and our load is disconnected. So to test this out, I'll turn this voltage on this down, and our cutoff was just over 3.1 volts. So when we get down to 3.1 volts, we hear a click, and that click was the relay. and you can see here we have no voltage now. So that's worked well. The other thing I want it to do, so I'll just turn this back up again. Now it's gone out and it won't come back again with the voltage turned up. I need to go and reset it. So you can see F8 there, that means fault 8, it means one of the cells has gone low. And if I reset it by doing this, then it's back to 20 volts on our load here. The other thing to do is just test out the communication. So the communications runs from the master through one of these wires, through each of these, and then back out and back to the master again. Which means that if we lose communications here, we've then lost our voltage information and we don't know what's going on. So I've got another fault code, another fault condition is that if I interrupt one of these, then after a few seconds, there we've run into a fault now, we've turned off the relay, and it's saying here that we've got a comms error. Module 4. If I reset this, that sounds like the fault has been reset. So if we have a comms error and then the error is reset again, it fixes itself, then it will turn back on again. So for my load, I want to discharge this over time. I don't want to do 100 amps like I did in my last test. I just want to do it reasonably slowly. And so I've started setting something up here. So I'll show you what I've done. I have this wire here. It's designed with a resistance, a bit like nichrome wire, but it's a slightly different stuff. And so you can see here that we have 1.73 ohms per meter and that it can take 2.21 amps. So what I want to do is to discharge at 2.21 amps through this wire. To do that, I need to get a certain length of it, and I need to figure that out by figuring out how many ohms I need at 20 volts to run 2.2 amps. So here we go, 20 volts divided by 2.21 is 9.04 ohms. So after 9 ohms, I've measured off how many meters I needed on that. It was something like 25 meters of wire. Wound it around here. Hopefully this is not going to get too hot for the wood, otherwise I need to rethink what I'm doing. But the resistance across here should be roughly 9 ohms. So just check my leads, they're about 5. And so yeah, we're roughly around 10 ohms, something like that. We're more or less where we need to be. So I think I'm ready now to connect in the battery here, and we'll see how much current we get. I'll need my clamp meter, won't I? Have my clamp meter, current meter set up there. I don't know how good it is at these low currents. It's measuring 0.16 when there's no current running through there at the moment. Okay, I think we're ready to start and see how this goes. I have my styrofoam there ready to see how hot this wire is getting. So we're now connected. We're running current through the wire. The clamp meter is reading something like 1.7 amps, and the wire is quite hot. Not hot enough to melt the polystyrene, so it's not terrible. It's not charring the wood. I can sort of hold my hand on it. Oh, I do have a thermometer here. What does this read? So that's reading 45, maybe up to 50 volts, 50 degrees. Oh, a bit higher up there. So I think that should be okay. The monitoring gear is on here. I've put this one onto the cell now. It was onto the power supply. And so our voltage is now 3.49 up to 3.50. Before they were from 3.50 to 3.51, weren't they? So it's just starting to go down. And it's logging it on the computer nicely, so I'll be able to tell later on how quickly it's discharging. It'd be nice to know how long this is going to take to discharge these cells to zero. Now, one way we can estimate this is to go back to our state of charge table from the similar cells. Now, I'm guessing that these are going to be something like 60 amp hours. So 60 amp hours, if we discharge from 100%, is going to take one cell 60 hours. We're discharging at 2 amps, aren't we? So something like 30 hours. If we're at 10%, then that's going to be something like 3 hours. 20%, about 6. So if we go with the 3-hour idea, then we've actually got 2 cells in parallel, so we need to double that to 6 hours. So I'm thinking sort of 6 hours is the minimum, maybe up to 12 hours for this test to complete. And unless I wanted to make it go faster, I could put in another one of those wires on the board. I could put another wire the same length and put it in parallel out there. That'll go twice as quick. So I've decided that I will put another lot of wire on this, another current discharge device. I've decided this time to try a bottle. It is hopefully a bit more heat resistant than the wood. Not that the wood's doing badly, but I've put slightly less resistance on the bottle as well. Slightly less wire, so it should get a little bit hotter. I've taped it on there with Kaptan tape. I've currently got this turned off, and so I'll just turn it on now. We have a bit over 4 amps now, rather than the bit under 2 before. So yes, this is definitely lower resistance. It's heating up there already. See how this goes. We're getting pretty close now. We're down to 3.19. We've got F3, that's fault 3. That means that we're getting low voltage, low cell voltage, so 3.19 is below the threshold. But we're not yet to the state where we're going to turn off the relay. So you notice the total voltage 19.1 volts. What that means is that we're now got a lower voltage at our load, which means also we've got a lower current running through. So our resistance has stayed the same, but our current is lower now because the voltage is lower, which means our load isn't steady throughout this test. It's going down. The temperature, by the way, it's up reasonably on this wood, but not nearly enough to make it burn. A bit higher on the glass. Can certainly feel some warmth in this area. I've also been checking the temperatures of the cells, and they have not moved whatsoever, which is what we want to see. So the 0% state of charge voltage value was 3.167. That's what I put into the BMS. We are getting pretty close. And the thing I've noticed is that we have gone very quickly down the last little bit here. But what we can see is that, yes, this does seem to be this chemistry. It's been more consistent up higher, and then it's come down quite quickly in this last little bit. So I think we are right at the bottom of the voltage of the cells. You can see at this low voltage that the difference between the highest cell and the lowest cell voltages, remember to start with they were exactly the same, and now the difference between the lowest and the highest is 0.02 volts difference. That's the sort of thing that happens with cells. When you discharge them right down, they can become a bit more apparently unbalanced. When you charge them up again, they'll probably be exactly the same again. There, heard it click. We're in F8. F8 is the low cell voltage. We now have 0 current. This means that we've finished our discharge test. Our battery is absolutely flat. And now what I like to do is to charge it up, and we'll keep a record of how much current we're putting in, how long it takes, and then we'll be able to see the capacity of our battery. I've set up now to do some charging. So here's a little power supply here, set to 25 volts. We'll get to that voltage in a second. But you can see positive and negative through the orange and the black are connected in, and so the black goes through into the isolator and fuse like it did before, and then into the module, and then the other one's out of the module through this relay and back into that larger cable there, back to the power supply. I've put the module off the trolley and onto the floor. This is because I'll be charging, and there's a slight chance that, you never know, I might get my voltages wrong and something might catch fire. I'm hoping that shouldn't happen. It's got the battery management system, which is set to turn off the charging via that relay whenever any of the cells get to a high voltage. I'm ready to turn this on. Let's just go through the voltages, how I selected the voltage. So since the discharge test did seem to pretty much exactly match this table, I've decided I'll charge up to close to the top, not quite to the top. I'll set it to 4 volts, which means I'll charge it up at a hopefully constant current, and when it reaches 4 volts, it'll turn off. The BMS will turn it off. Now, what I'm charging it with is this power supply. I've set it to 25 volts, which is 4.166. So it's the actual maximum cell voltage. Sorry, it's 4.166 times 6 cells. And so that shouldn't ever exceed that voltage. And if all the cells are balanced, then it shouldn't exceed the maximum in the table. But I've told the BMS to turn it off before we get there. What that will mean is this will be set to a higher voltage than what it is when it turns off. And so hopefully that'll continue to put the maximum current through there. If it was approaching the value, then with all these cables, we might not put the maximum current through as we approached our target voltage. So my idea here is to go up to 4 volts and then reassess, see how we're going, look at the graph, make sure everything looks all right before I do the last 10% or so of the battery capacity. Okay, so ready to start. Going up to 0.5 amp there, because this is set to 0.5 amp, so that's my current limit is set at the moment. Now, in theory, this is a 6 amp power supply. I don't think I've ever actually had 6 amps out of it, but we've got pretty big cables on, so let's see how we go. Oh, that's pretty close, 5.5 amps. So that's an interesting experiment. I've got another power supply there which can do 3 amps. Probably a better quality one. I might hook them both up in parallel, which means that neither of them are working quite as hard, because I'm imagining that if I run this for 20 hours at 5.6 amps, it might not like it. Here we go, our voltage has come up already on the cells, so I can clear that fault. So I've hooked up this power supply in parallel. I thought it was only a 3 amp power supply, but apparently it's 5 amps. It goes all the way up to 5 there, and we can see that this is measuring 5 amps here as well. I'd like 6 amps altogether, so maybe I'll put this one down to 3. And this one up to 3. And we've got pretty close to 6. At 6 amps, in theory, this should take, so if it's 60 amp hour cells, then it should take 10 hours to charge to 100% one cell. I've got 2 in parallel, and so it should take 20 hours. So into tomorrow. Here we are the next morning. We've been charging all night. The cells are still here, the battery's still here, which is a good thing. We're still charging at something like 6 amps. It seems to have gone down just a little. And both our power supplies are still saying 3 amps each. So we're still charging at full rate, and we've been charging at the full rate all night. So the module voltage 3.96 is the highest at the moment. So we haven't quite met our 4.00 target yet, but we're pretty close. Now we have been charging for 15 hours at 6 amps, and so that means so far we've put in 90 amp hours. If you remember, we've got 2 cells in parallel, so that's 45 amp hours each so far. I've been taking the temperatures of these cells every now and then. They've always been basically at ambient. So we've now reached our cutoff value. So it turned off at 4.16 and it's been sitting for a little while now. It's come down to 4.14 as the highest cell voltage there. Now, according to our table, 4.166 is the 100% state of charge. But what I found when I looked at the specifications sheet for the LG63s is that there's a standard charge which is actually to 4.20 volts. And so your standard charge up to 4.20, but then they say the 100% is 4.166. So I'm assuming that there shouldn't be much more above 4.166, but I'm going to try it anyway. So I'm just going to reprogram my BMS now to charge to 4.20. So there we go. That's programming now. Away it'll go. And oh yes, and so the highest specification, they say the highest voltage that you can have on those cells is 4.40. So we're still comfortably lower than that. We've now stopped charging at 4.20 volts in the highest cell. Now the standard charge, once you get to 4.2, you'll stay at that by reducing the current and just to keep the voltage constant until you get down to 3 amps. I didn't do that, I just charged at 6 amps until I got there and stopped, which makes my graph easier to work out afterwards. So that's why it's fallen down to 4.19. It'll probably fall down a little bit more over time as well. That went for about 3/4 of an hour, which means we've got a total of about 20 hours charging, which gives us about 120 amp hours. So that's 60 amp hours per cell. And so that means for that side of the module, so remember we were only connected to this side, and so there's a whole other side we haven't checked out. So that puts it at about 2.5 kilowatt hours, and so a little bit over, and so a little bit over 5 kilowatt hours for this entire module. To summarise, I bought these battery modules from a recycle place. They look like they're ex-vehicle batteries. There's 2 sections of them. They've got a cooling plate sandwiched in between those 2 sections. Each section has 12 cells. There's 6 in series, 2 in parallel, which means 24 cells altogether. Those cells I've worked out are around 60 amp hours capacity.
each cell. Each cell voltage is about you can discharge it to about 3.17 volts and charge it to about 4.20. Each side of the battery module has a voltage of 19.0 volts up to 25.2 volts. The capacity of each side is around 2.6 kilowatt hours, meaning 5.2 kilowatt hours approximately for the entire module itself. You can use the module, each side of it individually, or you can connect them together in series, or you can connect them together in parallel, depending on what you need. The cooling plate in between has a connector there so you can run coolant in between. In the weather we have, I reckon I'd be using the cooling plate to warm them to get a better capacity out of them in the cool weather. They have little sockets on there for battery management system. That's just voltage. There's no temperature sensors on these. And so I'd say we'd need a battery management system on here to monitor the voltages while we're charging and discharging. But also I'd want to stick some thermal sensors on the individual cells. So these metal plates here are in between each group of 2 cells, which means gluing a temperature sensor to these metal plates is going to be a good place for the temperature sensor. 5.2 kilowatt hours and 30 kilograms means that this is, and this small size means this is a very energy dense battery. This will be, I think, very good for my projects coming up. So I think I'll buy some more of these. There's a fair few of them at the recycle place. And stay tuned and you'll see what I get up to with them.